السلام عليكم، أهلا وسهلا. Are you fine? How are you? Okay, let me to start the lecture. I hope your friends attend to class. As soon as possible, because in there are concepts such as coverage criteria, coverage level, subsuming and subsumption, and test requirements, how these concepts help us in designing test values in our model-driven test design approach, and several techniques to use. Actually, two techniques to use coverage criteria in software testing, which means using test criteria as directly for generating test cases, or using them for evaluating the quality of test sets are discussed in previous lecture. In addition, we have talked about the four main structures that we use to define our coverage criteria in this book, which includes the input space partitioning or input domain characterization, and graph structures which is used by defining control flow graph, data flow graph, or other graphs in design documentations such as activity diagram and state chart diagram, or some other formal descriptions of information systems such as Petri net, graph transformation systems, are several tools which is used based on graph theories in mathematics. And the last two structures that are used in defining coverage criteria in software testing are discussed, which include logical expressions and syntactic structures, in which I said that each of these structures is discussed in a separate chapter. And by this example, we show how we could use, in this case, we mentioned two coverage criteria, the flavor and the color of our candies, to test the quality of a bag of candy. We see how the flavor subsume color coverage criteria. You know, we have color which has the same orange color. So candy we can mainly to push all covers in this set of colors. Several that have the same color term formally in previous lecture, and something criterion that we have mentioned means the flavor criterion and the color criterion. Discussed about these examples. We have defined the coverage level as the ratio of the number of test requirements satisfied by a test set T to the size of the test requirements. And we have done an example to show how the coverage level is computed in practice. Two ways that we can use the coverage criteria in software testing design are discussed again. As I said, the directly use which we could use the coverage criteria to generate our test values directly, or we can use the test criteria to evaluate the quality of existing test sets and use them indirectly to determine the quality of our test set, which is defined by generator and recognizer accordingly. These concepts are discussed in a previous lecture. This subsumption concepts of this is discussed again, and some advantages of coverage criteria, and what are the good coverage criteria, also discussed in previous lecture. And there are several PowerPoint slides in the later slides of these chapters. You can you can watch the video material of Professor Upwood for these slides, and I believe there are no any important concepts that we used in the remaining of the book. So I want to go to chapter 6, and if you want, you can continue to this reading by watching the video materials of Professor Upwood. So let's go to the next chapter, which is chapter 6. And we want to talk about input space partitioning or input space partition testing. Let me see your messages. Okay. Okay. If you have any question, please ask your questions. Okay, no question. Let me. Can you download here? I don't got it. Download what? Chapter 6, you can download it from the page of the second edition, this web page. You have introduced to this, and you can download your slides. Excuse me, this address is for but the page of this second edition of the book is this address, and you can download slides of chapter 5 and 6. Excuse me. Okay, no problem. Let me go to the next chapter slide. Okay. In this chapter, we talk about how we could use the input space partitioning technique to design our input values, our test cases, and how many coverage criteria are used by this technique, and what about them. The first structure we want to explain is the input space partitioning. As you know, when we have no any access to our source code or other software documentation, such as design UML models or other materials, we should focus on characterization of our domains to design our test values, and there are no any other possibility when, for example, especially in black box testing. So in this chapter we talk about the input space domain. In next chapter we go to the next structure, which is which could be applied to several sources such as source code, such as formal specification, design documentations, or our use cases. And in the chapter 8, we talk about the logical expressions. Also, this logical expression structure could be applied to several sources such as source code, finite state machines, and the specifications and DNF of our conditional statements. And the last chapter, we will talk about the syntax of our programs. So let's go to the input space partitioning technique. The benefit of what's the benefits of input space partitioning? As you see in this slide, the input space partitioning technique equally applicable at several levels of testing. For example, you can use this technique in unit testing to test your methods, your classes, or your objects. In integration testing, again, you can use the input space partitioning to determine the input values for your subsystems or your components, which includes of several objects or classes. And in system testing, again, you can use input space partitioning. So this technique is very important, especially when we have no access to any source code or design documentations or software under tests. So let me to go ahead. This technique, one of the characteristics of this technique is that it is easy to apply with no automation. It could be used easily by manually, and can adjust the procedure to get more or fewer tests. We could use this technique to produce, to design a lot of test cases or test sets, and no implementation knowledge is needed. As I discussed, it could be used when we are doing the black box testing. We use the input space. We use the domain of each input parameters of our product, or just we need a specification of our input values to design test value. So input domain is defined as all possible inputs to a program. For example, if you have a simple addition method, as we see in previous chapter, if we have a simple, for example, a compute average method, which compute the average of 3 integer values, even for this simple method, we have seen that there are 8 octillion different input combination values. Okay, so we define all possible inputs to a program as its domain. The domain of a program consists of all possible inputs of a program. Most input domains are so large that they are effectively infinite. Yes, this is true For example, approximately we could say that the input domain of our simple method, the simple compute average method in previous lecture, previous chapter, is infinite, because we never could test all of the 8 octillion combinations in practice. So we could say that this is infinite domain. Input parameters define the scope of the input domain, as discussed in the previous chapter. Each integer parameter defines about 2 power of 32 separate values. So parameter values to a method define our input space, data from file data, which could be read by a method from a file, define a piece of our domain, and global variable is the same, could define a part of our input domain, and even user inputs can define our input domains. So input parameters that are used to define our input domain includes parameter values of our methods in each of our classes, data which is referred from a file, which is read from a file on any storage, could be used to define our input domain. Global variables of our program, of our classes, could be defined, should be defined in our domain modeling, and so for user inputs. We partition input domains into regions, which we call blocks. We could use some characteristics of our domain, of our parameters, to partition the input space. For example, if we have just an integer parameter, for example, you have a simple method odd or even, which we want to detect if its input is odd or it is even. This method just has a one parameter. Okay. What characteristics of this simple method, the input of this simple method could be used to partition the domain? We could use the characteristics such as relation to 0 to partition the input of this method into 2 blocks, the blocks of negative value and the block of positive value. So this characteristic could be used easily to partition our domain, and we could test we could use we could test each block once, and we use each method. We use two test cases to test this method. Okay, and choose at least one value from each block. We do so for this example. Or as another example, suppose we have a method which has two alphabetic input character. Let me to type this example. For example, suppose we have some simple method m, which consists of two parameters. Each of one is of type character ch1 and character ch2. Okay, in this example, let me zoom. In this example, we have a method m and it has two parameters, both of them of are type character type. And suppose ch1 and ch2 just receives alphabetical letters. One prominent characteristics of alphabetical letters is the case of letters. Okay, if a letter is be a lowercase or uppercase. So by considering this characteristic of our input parameter, we could the domain of each of these parameters into two blocks. The block 1 includes all uppercase alphabetic letters such as this set, this subset, so on until capital Z. Okay, and another block or the other block consists of all alphabetical letters which has lowercase, which includes small a, small b, and small z. Okay, so by considering this characteristic of our input data types, we could partition the input values for each of these parameters into two blocks: the block of upper cases and the block of lower cases letters. Okay, so if we want to test this method, we could use at least one value of each block for each parameter. For example, a simple test case could be this test case. We give a capital A with a capital M as its parameters. Another test case could be a capital value such as D for the first parameter and a small or lowercase small, for example, n for next parameter. And another combination of our input space could be two small letters, such as small f and small g. Okay, and we could have another test case. Each of these combinations is a test case for this method. Suppose our method has two simple parameters, each of which is a character, is an alphabetic letter. So we could have several test cases to test this method by this model of our input space. We partitioned the input space of each parameter into two blocks. One block. Okay, so several all possible combinations by this partitioning could be this set of test cases. For example, the final is one of this set for the first parameter, the second parameter, such as small t with capital all combination. This excuse me, this is not all possible combinations, but for two in which each could select its value from two blocks, we have two times two combination format, and all possible combinations to test this method. In order to doing the complete test, we should test the application of these two sets. The Cartesian multiplication of these two sets defines all possible combinations to test this method. But in most cases, this is impossible to test all combinations. We just use some to be able to test this method, because the first test case choose both parameters from the first set, the second one choose the first parameter from the first partition and the second parameter from the second block, and the third test case choose the values of both parameters from the second block, the lower block from the set, and the last test case use the first parameter from the block 2 and the second one from block first. Okay. This could be this could give us some level of confidence about this method. In each combination, we have tested one combination of that type. One capital letter with another capital letter, one capital with one small, two small values are tested, and one small with one capital. Okay. So let me go ahead into for see your no sound clear. Miss Naima, please go to the second link. The first link is video for video materials, but the second one is for the homepage of the second edition of this book. This has go to PowerPoint slides page, and there are all chapters such as chapter 6. This is PowerPoint of the chapter 6. You can find all the PowerPoint slides of all chapters in this page. Okay. Let me come back to a slide. Inputs to a program. The input parameters could be defined by parameters, which is defined explicitly for our methods. But there are some input values which is not defined as explicit parameter. For example, the local variables of each class could be an input for all methods of that class. Okay, so we should consider those global variables as our input parameters. Or in some programs or some methods, we just receive file name or file address, and in the method we should open the file and read its material, its data. So all the data of that file could be our input values. Okay. Or some other inputs which is given by users are our input values. So we define input parameters as a set of all inputs defined by these four possibilities in programming languages. We partition input domains into regions. I discussed this by this example and choose at least one value from each block, and we do for you in this slide. So what's the meaning of partitioning domains? We define all possible inputs for a program as domain D, and we use some characteristics, or we use a characteristic of our input domain to partition the domain D into some blocks. We know partitioning by BQ. The BQ is blocks of the partitioning, Q partitioning. Blocks of the Q partitioning, which includes a set of all partitions or all blocks. We name blocks by the small b, and we named all partitions, the set of all partitions, or all the partition Q by capital B with the Q letter. Q is our partitioning technique. So BQ, let BQ be a set of all possible blocks according to a specific characteristic, such as relative to 0, such as lowercase and uppercase for alphabetical letters, and some other characteristics in other data types. So the partition must, our partitions must satisfy two properties. There are two properties in input space partitioning. The first one defines the disjointness of these blocks. As you saw in this example, we partition our input domain into two disjoint sets. This set share nothing with this set. These sets are disjoint. And the intersection of these sets is an empty set with no any element. Okay, so the first condition of a correct partitioning is that our blocks, all pairs of our blocks should be disjoint sets, pairwise disjoint, no overlap. Okay, and the union of all these blocks should make the domain D. This is set the completeness of our partitioning Q. Together the blocks cover the domain D, which means the union of all of the blocks make the domain D, make the set D. This could define easily the completeness feature of partitioning technique. So each partition must satisfy these two properties. As you know, by partition each domain, we define some equivalent classes. We have some equivalent of this block is a class of values. And to test or put one value of each of these blocks. Okay? Suppose have a domain D. We partition this domain into three B1, the block B2, and the block that for all disjoint blocks in our Q, the intersection of BI with BJ should have no element, should be an empty set, and this define the disjointness of any pairs of our blocks, the pair B1 with B2, B1 with B3, and B2 with B3. And as shown in this picture, you see that there are no overlaps between each two pairs, each two blocks. Each pair of these blocks have no an intersection. Okay, this defines the disjointness condition, and this union of all of our blocks should make the domain D should be equal the D. So the union of all blocks of BQ should make the domain D. This defines the completeness condition. So if we want to partition any input space, we should be aware of, we should be cautious about how to use any characteristics of our input parameters to have to be used partitioning by and keep these conditions true and don't violate any of them. Okay. Using partitions, choose a value from each block. It's traditional, it's trivial. Each value is assumed to be equally useful for testing. When we partition this domain by a specific characteristic, then all values in block B2 has the same effect with each other value in this block. So it's not matter to use one of the values in this block. We randomly select one value from this block to test our method, and this is so for each other blocks. Okay. How we make partitions, forming partitions, or we can make our partitions. First of all, we should find some characteristics of our inputs, such as case of letters, such as related to zero value for integer value, some semantic, such as each parameter. Okay, we will see all types of characteristics in this chapter soon. So by that characteristic, by the selected characteristic, we could partition our input domain into some blocks and choose tests by combining values from blocks. In the previous example, we have two parameters of the same data type, and these two parameters have the same input domain, and by the characteristic case of letter, we partition the input domain into two blocks, and we make some combination, some test cases by choosing any value of each block in each combination. For example, we made 4 test cases to test this method. So if we could partition our domain into its blocks successfully, the second step is to selecting some combinations of blocks from blocks as test cases, and we will define some coverage criteria in this chapter to several combinations as our test cases. There are some extra characteristics that could be used in domain space partitioning. For example, whether an object should receive an object as its parameter, the relative to null value could be a characteristic of this input parameter to partition the input value into two blocks, a block with a null value and a block with all other non-null objects. Okay, another characteristic is the order of elements of any list F. For example, if the input list is sorted or inverse sorted or in arbitrary order or so on. And other several characteristics that could be used in domain space partitioning. How we choose partitions? Defining partitions is not hard, but it is easy to get wrong. There are some situations we simply get wrong partitions. We should be cautious about these situations. For example, when our characteristic for partitioning is the order of elements in a list F. Suppose we define 3 blocks according to 3 different characteristics. For example, sorting in ascending order, sorted in descending order, or block by arbitrary order. How about this partition? Are these partitions is correct? Are these blocks define a correct partitioning? Correct partitions? As I said before, we should keep 2 conditions true. The first condition is disjointness of our blocks. Are these blocks, the block B1 and block B2, are disjoint sets? You think these two blocks are disjoint? These have no intersection. Suppose we have a list with just one element. A list with just one element could be placed in this block, in block P1, and also we could place it in block P2, because a list with just one element could be supposed as ascending order, sorted list with ascending order, and also we could suppose it with sorted with descending order, because a list with one element is a sorted list, and we could say it is sorted ascending or sorted descending. There is no difference between these two orders for a list which has just one element. So this characteristic could not partition our domain into disjoint sets, disjoint blocks. So it's a problem. It's fishy. Okay, what if the list is of length 1? The list will be in all 3 blocks. We also could place the list with one element into block 3. Because we could consider no order for a list with one element. So these blocks overlap with each other, and the disjointness condition is not satisfied. It's violated by a list with one element. Okay, what's the solution? There are 2 characteristics in this case that address just one property. Okay, in this case, the problem is that we have used 2 characteristics which both define one property. So this is the problem of our partitioning. For example, if we use characteristic 1, list the sorted ascending, each list could be sorted or not. For example, block P1, this characteristic is true for block P1, and it's false for block P2. Okay, and the second characteristic could defines the same property for these 2 blocks. These blocks have overlap with these blocks. In this case, we have used 2 characteristics to partition and defines no disjoint partitions. So we should be cautious about defining characteristic of our input parameters to define disjointness partitions and the union of all partitions should make the complete, the universal domain, the domain, which defines the second condition as completeness. Properties of partitions. If the partitions are not complete or disjoint, that means the partitions have not been considered carefully enough. And we should revise these. They should be reviewed carefully to make them disjoint. The domain may use any modeling, any design activities. Different alternatives should be considered, and we model input domain in 5 steps. Please note these 5 steps to see how you could model a domain, the input domains. We have 5 steps to model input domain. The step 1 and step 2, in our methodology, some of these steps are located in implementation abstraction level, and some of them are located in design abstraction level in this model-driven test design approach. So the step 1 and step 2 should start by the software artifact, which is located in the implementation level. If we use the source code, the step 1 and step 2 move us from implementation abstraction level to the design abstraction level. We talk about the step 1 and step 2 in next slides. We talk about with more details in next slides. And the steps 3 and 4 are entirely at the design abstraction level. And step 5 brings us back down to the implementation abstraction level. These say about the walking through this procedure. We could, in chapter 6, 5 steps are defined to partition or model input domain, which walk through this process. The step 1 and step 2 is defined in this level of abstraction, step 3 and step 4 for this level of abstraction, and step 5 come back to the implement to see these steps. In step 1, we should identify each testable entity, each testable functions of our program or of our system under test. For example, individual methods could be one testable function. Each method, each independent method could be one testable function. Or methods in a class often have the same characteristics. Why? Why these items say that methods in a class have the same characteristics? Why? This is because usually all methods in a class uses the attributes of that class, and attributes of that class are shared between all methods. All methods of a class could use all in common. Okay, so the characteristics that could be used to partition input values for those attributes is the same for all methods of a class. Okay, so the method, we could say the methods in a class often have the same characteristics. And when we talk about a program has bigger granularity in compared with methods. Okay, a program could have several classes or several methods. So programs have more complicated characteristics because they have more input parameters, more input attributes. They share more files, and they have more input, user input values. So modeling documents such as UML documents, UML diagrams could be used to define the characteristics to be used in input domain partitioning. And then we do system testing. As you know, systems could be integrated from hardware components and software components, and they have received several input types from several devices, users, operating systems, and other subsystems. So there are a big domain or domains for in doing system testing. Okay. So in step 1, we should identify testable functions. Even we do a unit test or we do integration test or even we do system test. We should identify testable functions. In the second step, according to the set of functions detected in step 1, we should find all parameters of those functions. We should find all parameters of those functions. And this step could be done easily, often fairly straightforward, or even mechanical. You could do this mechanical. There is no problem. We receive a set of functions, and their input parameters are defined explicitly, and shared attributes are defined in step 1. So we should find all parameters of our program. For example, in method parameters and state variables. The state variables is the state attributes, the attributes of the class, of the corresponding class. Okay. And in components, parameters to methods and state variables define all possible parameters for that component. And in system testing, we should define all inputs of a system including files, databases, and user inputs, and inputs of all methods defined in that system, which could be called directly by our users. Okay. In the third step, and the most important step in input domain partitioning, we should model the input domain. The activity of partitioning of input domain is called by this keyword. Model the input domain means partition the input domain. To partition the input domain, as I said, we should use several characteristics of all parameters and define several combinations of input types, input values, and select among them our test cases. So the domain is scoped by parameters. The structure is defined in terms of characteristics, and each characteristic is partitioned into sets of blocks. For each parameter, we use a characteristic to partition its domain into some blocks. Okay? And each block represents a set of value with the same importance. There is no priority for any value of each block. All values located in the same block have the same priority for test. Okay, because we have made that block by our selected characteristic, and values with another importance is located in another block. Okay, this is the most creative design step in using input space partitioning technique. It's obvious. And in the step 4, apply test criterion. Okay, in this chapter, probably in next session, we will define some several criteria for choosing combinations of our input values. There are several criteria in input domain, input space partitioning technique. Okay, a test input has a value for each parameter. Okay, in a test case, for each parameter of our method, of our component, or our system call, we should provide a value for each of its parameter. So the value of it in one block, its partitions. Randomly, we select it randomly from one block of its partitions. Choosing all combinations is usually infeasible because all combinations could be infinity. There are several parameters, and for each parameter there are several blocks according to each characteristic. Compute the Cartesian multiplication of all sets of blocks defined for each parameter type. Okay, So coverage criteria allow us to subset of all combinations, a subset of all combinations. So we need some coverage criteria in this chapter to use this technique effectively. Okay. And in step 5, we define combinations of blocks into test inputs, which give us back to the implementation level of abstraction, and we could test each method, each component by these test inputs. If we could define its expected results and prefixes and as I defined. So in step 5, we should choose from each block. As I said, there are no any priority for each value of a block. So all values located in a block have the same chance. But 2 contains 2 methods. What's the interface 2? The slides. Let me see the clock. Oh, so if you have any question, please ask your question. And in the next session, we will discuss about the latest we have this chapter to discuss in the class, and we have discussed just 10 slides in this session. Next will be this chapter, and we have 3 more chapters to teach. Each of one probably need a week. Okay, if you have no any question, let me finish this session, and it's enough for today. في أمان الله. See you next session.